On this video, we will talk about infinite geometric series. So let's start by looking at this small introduction question which says, let's take in consideration a geometric sequence, let's call it A of n, and an infinite geometric series, let's call it sigma of A of n. And the question is it possible for an infinite geometric series, again, sigma A of n, to converge? Well, it doesn't matter if it's geometric or arithmetic, any infinite series, it converges if the sequence of partial sum converges. In other words, if we would align the first partial sum, the second partial sum, the third partial sum, the fourth, the fifth, the sixth partial sum, and so on, if we would align the values of those partial sum and we just list them in a sequence, if we see that the sequence is converging, then we can say that the infinite series is converging. But now, let's try to understand what we're trying to do here. We want to say if a geometric series, when does a geometric series converges? Well, we know that the partial sum, the sequence of the partial sum must converge. So, in the value of the partial sums are, they come from the actual values in the sequence. And I guess this is the seventh term. Now, if this is a geometric sequence, we know that in order for me to get from one value to the other, I must have multiplied by some ratio. Because again, we're taking a look at a geometric sequence. So therefore, the only thing that really dictates the behavior of the geometric sequence is the value of r. So perhaps we have to take a look at the value of r. Is there any way where, or is there any situation where the value of r will dictate if the sequence converges or diverges? Well, another point that we made on our previous class is that the sequence of partial sums converges if the sequence converges to zero. In other words, if we take a look at the value of the terms in the sequence, and we see that those values are getting closer and closer to zero, then we can assume that the partial sum sequence is going to converge as well. So when will our sequence will start approaching the value of zero? Well, there can only be two situations, where the first situation is if the value of r is less than 1. Therefore, if you keep multiplying by a decimal that is between 0 and 1, that decimal is going to get, or the values that you're getting out are going to get so small that they're going to be approaching to 0. And also, we could have another situation if r is greater than -1. So, in other words, either if r is bounded between -1 and 1. And this is the only way where a geometric sequence or a geometric series will converge. If we take a look at the sequence, the geometric sequence, and we look at the actual ratio, the common ratio, I should say, if we take a look at the common ratio, if that common ratio it's bounded between -1 and 1, and notice that I'm not including 1 and -1. if that common ratio is bounded between -1 and 1, then we can assume that the infinite series of that sequence is going to converge. And this is very important. And this is the main idea that I wanted to get from here. If your common ratio, if the common ratio of the sequence is any number between -1 and 1, then the infinite series of that geometric sequence is going to converge. So now the question is it possible to find an equation that perhaps we can define to represent the sum of infinite terms in a geometric sequence? Well, it just so happens that there's one. So since I know that the geomet or any series is being determined by the partial sum, so let's just write down a very standard way of the geometric partial sums. So here we have the sum of some geometric sequence. Let's call it a of n equals to 1. And if we assume that a of n it's a geometric sequence, then I know that my first term is my first term. Then the second partial sum is going to be the first plus the second term. Then the third partial sum is going to be the first plus the second plus the third term. And notice that all I'm doing is, if I'm taking the infinite series, I'm just adding all the possible terms. So a of 1, r of 3, a of 1, r of 4, a of 1, r of 5, and so forth. So this is how we can define the infinite partial sum. It's just saying, I'm just going to add all the possible terms in this infinite sequence. And just like we did in our previous lesson, I'm just going to manipulate this expression. And I'm going to say, okay, fine. The infinite partial sum is just the addition of all the possible terms. So I'm going to define something else that I'm going to name R infinite partial sum, which all it is just getting every single term in the infinite series and just multiply it by R. So therefore now my first term in this sum is going to be a1r. Then my second term, it gets multiplied by r, so now this becomes a1 r squared. Then my next one is a1 r third, so it's just the third term multiplied by r, you get this. The fourth term multiplied by r, you get this. The fifth term multiplied by r, you get this. And the fifth term multiplied by r, you get this. And again, it's infinite, so it just continues without a bound. So now that I have these two expressions, what I'm going to say is, okay, look, I kind of have an explicit way of writing those expressions. So I'm just wondering, what would happen if I get all the terms in my first partial sum and I subtract it by the actual values that I got in my second partial sum? So what is this exactly equal to? So what if I get all the terms in my first partial sum and I subtract the terms in the R infinite sum? So if that is how we're subtracting, well, notice that the first term is not going to get canceled out. But now if I get this term and I change this term to be a negative, notice that they're going to cancel out. And then the next term, if I subtract it, now notice that this becomes a negative, and now this is going to cancel out. And if we continue this, you know that this term is going to cancel out with this term. This term is going to cancel out. This term is going to cancel out. The next term is going to cancel out. And now all the possible terms that are going to come after that are going to cancel out with each other. So the only term that quote unquote survives out of all the cancellations is just a of 1. So now notice that I have an expression now. So if I take the partial sum and the infinite partial sum, and I subtract r times the partial sum, that's equivalent to the first term. But I noticed that I wanted to get an explicit way of writing an infinite partial sum. So therefore, if I take a look at my expression on the left hand side, I can kind of like can't bring it out. I can factor it out. So therefore, if I factor out the expression s of infinity, I get 1 minus r. And if I want to get s of infinity, all I got to do is perhaps divide it by 1 minus r on both sides. That way this expression cancels out. And now I get an explicit formula that I can use to define the infinite partial sum. So for any geometric sequence, if I add an infinite amount of terms, that's always going to be equivalent to this expression where a of 1 is the first term and r is the common ratio. It is a very good conclusion to understand because all we're saying here is that if I want to take a look at a geometric sequence, if I and an infinite geometric sequence, and if I add infinite amount of terms in this sequence, that's always going to be equivalent to this value, the value that we're going to get by just getting the first term and then dividing it by 1 minus r. So this is a very good thing to understand. The idea of adding infinite terms and the addition of infinite terms being equivalent to the single value, the first term divided by 1 minus r. Now, when will the infinite geometric sequence formula work? Well, if we go back to our introduction, we already answered this question because we stated that for any geometric sequence, the partial sum is going to converge if the value of r is bounded between -1 and 1. So therefore, the infinite sum it's equivalent to a value if the sequence converges. And the sequence converges only if r is between -1 to 1. So if we take a look at a geometric series, and if we see that the sequence has a common ratio that is greater than 1, then we know that that series is not going to converge. So therefore, it's not going to be equivalent to a value. But if we see that the value of r in the infinite geometric sequence is bounded between -1 and 1, is any value between -1 and 1, then we can use this formula to see what value will the series converge to. And the opposite, so when will the infinite geometric series will not work, or the formula for the infinite geometric series will not work? Well, it will only not work if the sequence of partial sums diverges. And the only way that this can happen is if r is less than -1 or if r is greater than 1. Because I know that in order for the sequence to converge, r must be between -1 and 1. This formula does not work if the sequence diverges. And the sequence diverges if it's any value that is less than -1 or greater than 1. So this is a good explanation as to how the formula that we do have for the infinite or the sum of an infinite geometric series. This is what we call it. This is the sum of the infinite geometric series. It's a formula. Now, let's use it. Okay? Let's take a look at some examples. Let me just bring this down. So now we want to find the sum if it exists for the following series. And again, we're going to assume that they're all geometric series. Okay. So the first term of an infinite geometric sequence is of a value of 3, and the common ratio is 2 over 4. So we're saying that A is equals to 3 and R is equals to 2 over 5. Now, the first question that we should try to answer ourselves is, well, is this sequence convergent? Well, let's take a look at the value of R. R is 2 over 4, 2 over 5. So therefore, in this case, yes, R is between -1 and 1, 2 over 5, which is approximately zero point 0.4. So now notice that zero point 0.4 is definitely between -1 and 1. So now we know that the sequence will converge. So therefore, the series, the infinite series, must have a value. And what is that value? Well, the infinite sum is equivalent to the first term over 1 minus r, which in this case, we know that the first term is 3, and 1 minus r is zero point 0.4. And if we put this in a graphing calculator, the value that we're going to get out is 5. So what we're saying is that if we have an infinite geometric sequence and I add all the possible values in that sequence, the output is going to be 5. Let's do a couple more examples here. So again, here we have the explicit way of writing a geometric sequence. And again, if you recall the explicit way of writing a geometric sequence, it's always going to be a1 times r n minus 1. So therefore, by the way that this is written down, I can assume, or we can see that the first term has a value of -7 and the value of r is 0.23. So now the question is, can we use the infinite geometric sum formula? Well, r is 0.23, which is definitely between -1 and 1. So yes, since r is between -1 and 1, then we can find the infinite sum. So let's find that infinite sum. We'll recall that the infinite sum is a1 1 minus r, where a1 is -7, 1 minus, and r is 0.23. And if we were to compute this in a graphing calculator, we would get a value of 100, -100 over 11. So therefore, if I would have listed all the sequences from this geometric sequence, and if I were to add all those numbers, I can assure you that it's going to be not perhaps equivalent, but it's going to be pretty close to the expression of -100 over 11. Let's just finish it up with example D. Again, if we take a look at the way that my sequence is written out, I want to know, well, if I add all the terms in this sequence, what value is it going to approach? Well, first notice that the first value is, not infinity, but 8, and the value of r is 5 over 4. So is it true that we can use the formula that we just discussed a couple minutes ago to find the infinite sum of this infinite geometric series? Well, notice the value of r. It's 5 over 4, which this does not. So the value of r does not meet the condition of r being bounded between -1 and 1. And if it's not meeting this condition, then therefore the sequence diverges. And if the sequence diverges, then the series must diverge, which in this case, we can say that this series diverges, and therefore there is no finite sum. And this concludes our lesson for the infinite geometric series.